Hello, everyone. Welcome to AREC 333, lecture 29. Today, we will continue with risk in production. The outline for today will first, I will spend some time on the risk measures, which is variance and standard deviation, which is the square root of variance. So I will go over how you can what's the definition of variance and standard deviation and how can you calculate it. I will also spend a little bit of time here talking about the difference between population variance and sample variance. You are not required to fully understand the difference between those two, but based on last year's teaching experience, students were often confused about those two. So I feel like I should spend a little bit of time on that. And after that, we will continue with the canola and weight example. And then use that example to calculate the variance. And that will lead us to the producer's preference over canola or wheat. So one of them is a little bit riskier than the other, depend on what's the risk measures. So then we need to introduce two more concepts of certainty equivalent and risk premium. So those two concepts will help us understand the preference over different risky outcomes and also help with decision making when there's risk in production. So in addition to chapter 1 of Hardeker et al. 2004, here the certainty equivalent and risk premium content is covered in chapter 5. So if you feel like the lecture slides is not enough, then you should refer to that chapter. So first, let's continue with variance and standard deviation. We barely started with variance in last lecture. We did talk about mean or expected value in last lecture. And that is more about the central tendency when you have the risk outcomes. So variance here, it is another measure of risk. So usually we are not only interested in the central tendency, we are sometimes interested in the dispersion or the spread, or sometimes you call it variability of the values of X. So remember, X was the outcome. So for example, in the milk yield example, it is the different ranges of the milk yield. So usually the greater the dispersion or the greater the spread, then the greater the risk. So usually we use variance to describe the dispersion from the expected value, or we may call this mean. And if you take a square root of the variance, and we sometimes also use standard deviation, and we use a letter sigma to denote the standard deviation. So I have an example here. If you have took statistics course, you must know this distribution, which is the normal distribution. So I have arrow here. So that arrow is mirroring the spread of this distribution. And as we mentioned, the more dispersion or more spread, then the higher the risk. So to give you an example here, I will come back to this normal distribution and graph after I introduced the mathematical calculation of variance and standard deviation. So, but here, just to give you a feeling of what is a greater risk. So I have here two different distributions. And there's the red one and the blue one. So both distribution have the same mean, or here it's called average, which is not precise. So I would rather call it mean. So both distribution have mean equal to 100, which means that the central tendency is the same. However, those two distributions, one is having higher risk than the other. So the blue one here, I already denoted that it's associated with a higher risk. It is having a higher standard deviation than the standard deviation of the red distribution. So you can tell from this graph here that the blue distribution is having a wider spread or dispersion than the red one. So that one is having higher risk. So how do we exactly calculate the variance or the spread or the standard deviation of a distribution? So this is the definition of variance. Variance is also a expectation. However, it is an expectation of the squared deviation of a random variable from its mean. So in order to calculate variance, you first need to know its mean. And here, let's look at the mathematical expression here. So V is VAR, X is a random variable. When we say random variable, which means that variable can take a lot of different values. And each realization we use this xi, and each realization is associated with a different probability. So you can think of this xi in the milk yield example of, for example, it's between 7,000 and 7,100, the yield. And then there's a probability PXI associated with that range. So the milk yield X is a random variable and it has different realizations. So the variance is the expected value of this X minus its mean, or the expected value of X, and then you take a square and calculate that that expectation. So here is a discrete way of calculating the variance, which is usually what's required in this course. And suppose you have n different outcomes, then the variance can be calculated as the probability of xi times this squared deviation. So this, if you compare it with the definition of the expectation, it is both the summation of the probability of xi happening, and then what's difference is here. So when you're calculating the expected value of x, then you put xi here. However, if you're calculating the expected value of the squared deviation, then you put the squared deviation here. So both variance and mean are expected values. The difference is what's there that's timed by the probability. So if you simplify this expression here, then you can get this variance is equal to the expectation of x squared minus the square of the expectation. I will derive this in a little bit just for those of you who are curious, and you can also just trust me and use this expression to calculate the variance. And before that, the standard deviation, once you calculated the variance, then you can just take a square root, and that will be the standard deviation. And going back to this normal distribution graph, here from this mu is the mean, is the expected value of x, and this range I just put it here. This is 1 sigma. So sigma will be the standard deviation. And what does this mean for a standard normal is that between the mean and the one standard deviation to the right of the mean, then the probability, as we mentioned in last lecture, is the area under the PDF curve, the probability density distribution curve. So this whole area for this range, then the probability is 34.1. That is the probability in that range. And as you can see, for normal distribution, if you were within plus and minus 2 standard deviations of the mean, then the probability of that is very high. It's close to 95%. So the outcomes happening in the 2 standard deviation range around mean is around 95%. So that is the standard deviation. And imagine that if you have another normal distribution. So this should be above here. So here, like this. Then for this distribution, in order to have 34.1%, then this standard deviation, assume this is again the mean, then this is sigma, let's say sigma prime. This sigma prime will be smaller than this sigma here. So for this distribution, the sigma, the standard deviation, is smaller than this one. And also the risk of this one is also smaller. So that's why we're saying that the standard deviation or the variance is a good measure of the risk. So variance is the expectation of the squared deviation of the random variable from its mean. Let me actually derive here the expression which I have just mentioned. It is equal to this one. So if you just trust me, that's the outcome. You can probably skip the steps I'm showing you here, or if you're curious, you can bear with me and go through these steps. To derive this expression, we first need to use the definition of expected values. So here, let's use this here to calculate the expected value of that squared deviation. It is actually equal to the summation of the probability of xi happening times the squared root of xi minus the expectation of x. So here, put it here. And that is the definition of expected value. And we can further expand this square here. So here we can have it equal to from I to m p x I times, so in the square we can have it as 2xi squared minus 2xi times ex, and then plus ex squared here, and we can do the summation over the three terms here. So here we will have the summation of pxi times xi squared and minus, I will put 2 in the front since it's not affected by the summation. And then here I have pxi times xi times expectation of x. And then finally, we have this summation of pxi times ex squared. I will just write e squared to save notation. So here, this term, by the definition of expectation, this is the expectation of x squared. And the second term here, this e is a constant, so it can be moved to the left, outside of the summation. So it's 2e times this summation pxi times xi. Here, again, by the definition of the expectation, this is the expectation of x. So I will just replace it with the expectation of x. So this is the expectation of x. And here we can move this e squared to the left-hand side, or to, to the outside of the summation. So then we are left with this expression here, and by the property of probability, we know that for all of the outcomes from I equal to 1 until n, then the summation of the probability is equal to 1. So you can think of xi here as 2 outcomes. So n equal to 2, I equal to 1 is bad weather, I equal to 2 is good weather. And the probability of them happening is 1/2. So if you sum those two probability, it should equal to 1. And also for the milk yield example, it's also the same. If you sum over all the probabilities, then it should be equal to 1. So here, since it's equal to 1, we can just skip writing it. And here, those two, we can actually further simplify it to minus e squared. So again, here this e is ex. So we ended up with this expression here. So the variance is just equal to the expectation of x squared minus the square of the expectation. This slide is just the derivation process that I wrote down, and I'm keeping this here for your reference in case you want to come back and verify this result. So I mentioned that I do want to spend a little bit time talking about the difference between sample variance and population variance. For those of you who took the statistics course, you probably have heard of those two terms, but don't worry if you haven't took the statistics course. So I will just give you an example so that you have hopefully you will have an understanding of what is population and what is sample. So imagine that you want to know the average height of all the people live in Canada. So in order to get the average height, you have to measure every single person's height here in Canada, and the Canadian population is the population here. Usually it's not practical, or sometimes it's not necessary to measure every single person's height. Instead, we just draw a sample. For example, we might take 5% of each city's population and measure their height, and then use the sample average to kind of get an estimate of the population height. If the sampling process is a good process, then the average height you get from the samples should be very close to the population height. So as your sample get larger and larger, if instead of 5%, you decided to do 50%, then your sample average should be very close to population height. And if you decided to do 100% of the population, then your sample is the same as your population. So that's a difference between a sample and a population. And in your statistics course, you probably were told to calculate a sample variance. And here, so usually when you calculate the variance of a sample, use the formula I have just shown you in the previous slide, then the variance you got from that sample usually is a biased estimator of the population variance. So it's okay if you don't understand here what is a estimator. So basically you calculate the sample variance and then you say, okay, then the population variance is also should be the same, but usually that depends on the size of your sample. So here I want to emphasize again the difference between the sample variance and the population variance in terms of their mathematical expression. So again, here, assume you draw a sample from the population. For example, you decide to take 5% of the population and do your analysis for that 5%, and that is your sample. So assume here, to make our life easier, let's assume the probability of y1 until yn, the probability of each of those happen is the same. Then we can calculate the expectation of that sample. So the probability of each yi happening is 1 over n. And this is only the simple average here, the expectation. And you can also calculate the variance of y. So remember here, y is the sample. So the variance of y we can calculate using the formula I have just provided to you. And we use sigma y here. I put a subscript y here to indicate that this is the variance for the sample y. And if you took an expectation of that sample variance, and the way that you took expectation is the same as we calculate expected values in previous slides. So if you took the expectation of your sample variance, then you will be able to get this result. I don't want to do all the derivation here, calculating the expectation of the sample variance. It's not the focus of this course. If you're really curious, there are many statistics books or courses that you can refer to, but here you just have to trust me that if you take the expectation, then you will get this result. So here, the sigma square is the variance of the population. So if you want to measure the height of the whole Canadian population, then the whole Canadian population is your population, and this sigma square is the variance if you did measure every Canadian's height and then calculate the variance. However, usually that's not practical. We took a sample, and this is the sample variance. So if you took the expectation of this sample variance is not equal to the population variance. It is biased, and it's biased by this fraction here. So again, this is your sample variance. This is your population variance. Usually in statistics, if we want to correct that biasness, we usually will define a bias corrected sample variance, and you probably have saw this S square, this small S square in your statistics books. So this is a bias corrected sample variance. So in order to make sure its expectation is equal to the population variance, then you have to multiply by this n-1 over n here. So if you multiply this term with this term here, then it's equal to 1. So a lot of the times when I asked in this course for last year, when I asked the student to calculate the variance, the sample variance, then a lot of students calculated this one. It's not wrong, but I don't think many of the students understand the difference between this S square and this sigma y square. So the focus of this course is not to come up with an unbiased estimator of the population variance. So that's not the focus of this course. So in AREC 333, if I ask you to calculate variance of some data that I give you, then you simply need to calculate this one. There's no need to correct for the biasness of this estimator. So it's okay that you just calculate this variance. You don't need to do one more step here. So that's, I hope I make it clear the difference between sample variance and the population variance, and also why we, in statistics, why we sometimes use this bias corrected sample variance. So that is more for the estimation of this population variance. Let's continue with the canola and wheat example. And first is let's try to calculate the variance here. So we have the outcome is good weather, bad weather, I equal to, so here we can say I equal to 1, I equal to 2, and the probability of those happening are both 1/2. So for canola, the X, so here is X1. Or maybe we can use C1 here. So C for canola, C1, C2, and this is W1, W2. So this canola, if good weather happened, the profit is this much, and bad weather happened, the profit is this much. And last time we already calculated the expected profit. So today, let's continue with the variance. So variance again equals to sigma squared. Sigma is the standard deviation. So it is equal to the expected value of the squared deviation. And we can just use this expression to calculate the variance. It's a little bit easier to do. Okay, so here I used this expression, and I can also show you a different way of calculating the variance. But first, let's use this expression. So to calculate this, it is the probability is 1/2 for good weather. And when good weather happen, xi or cy equals to this number. This is the expected value of c. And you take a square plus the probability for bad weather, and then the profit for bad weather minus, again, the expectation. So this is using this expression here. And if you do all the algebra here, you will be able to get that number. And a different way of calculating this is using this expression. So to use that expression, it is simply the probability times 16,000 squared and plus the probability of bad weather, and then times 4,000 squares. And you have to minus the square of the expected value is 10,000 squared. And if you do this calculation, you should get exactly the same number here, this number here. So let me know if you get a different answer. That's how we calculate the variance. And one more practice here is you can also calculate the variance for growing weight. And that way, I will not do the calculations here, but you are welcome to verify this result. And you should also try to calculate the variance. For example, if the probability are not equal likely. For example, if good weather is happening with probability of 2/3 and bad weather is happening with probability of 1/3, then what is the expected profit and what is the expected variance and standard deviation? So you should try to use this unequal likely probability to do your calculations and see if you're really able to calculate variance. Once we calculated variance, then it is very easy to get the standard deviation. So variance is sigma square, and we know that from previous slides, the variance of canola is 6,000 square, and variance of weight is 1,000 square. And the standard deviation of canola is just 6,000 that you took square root of the variance. And similarly, the standard deviation for weight is 1,000. So we calculated both the mean and the standard deviation of canola and weight. And now we can probably do a comparison here. So the producer is deciding to grow canola or wheat, and based on expected profit, canola is having a higher expected profit. However, the standard deviation of wheat is lower, which means wheat is less risky. So given the assumption that most farmers are risk averse, so the farmers then should grow wheat, which is less risky. But canola is having higher expected profits. So what should the farmer choose here? Canola or wheat? And it turns out that we need some decision criteria to help the farmer or the grower make the decision. Generally, the farmer or the grower is trying to maximize the average or the expected profit, while at the same time ensuring that the risk taken are not too high. So those two factors the farmer need to balance. However, which one is having more weight? It depends. It depends on the attitude of the individual decision maker. So one farmer might prefer to grow canola, and the other farmer who is more risk averse might prefer to grow wheat. And it also depends on the financial reserves available to cope with bad times. So if the farmer is having a lot of cash at hand, then maybe the farmer will be able to cope with risk better, and that farmer might prefer canola. However, if the farmer is really risk averse, and that farmer might prefer to grow wheat. So let's take a look at the preference over risky outcomes. And I'm taking canola here for example. Suppose now there's an insurance available on the market. So if the farmer is not buying insurance, then it is just going to be what we have described. There's a 50% chance that the farmer will get a profit of 16,000, and there's another half chance that the farmer will get 4,000 if bad weather happen. However, with the insurance, if the farmer buy insurance, then the insurance company will say that no matter what happens, I will pay you $10,000. So pay attention here. This $10,000 is just the expected value of this of the profit for growing canola. So if you took 0.5 times 16,000 plus 0.5 times 4,000, then this is equal to 10,000. We showed this before. So if the insurance company is offering this, and one particular farmer, let's assume there's one particular farmer. If the insurance is offering this payment, then the farmer will decide to buy insurance. And the insurance might have a different offer saying, I'm not paying you 10,000, I'm paying you 9,000 for sure, no matter what's the weather. And this particular farmer still decided to buy the insurance. However, when the offer lowered to 8,000, the farmer is indifferent between buying the insurance or taking the risk. So if the farmer is not buying the risk, then here is what's going to happen. However, if the farmer buy insurance, this is what the farmer will get for sure. And if the insurance is offering to pay 7,000 for sure, then this farmer decides, I'm not going to buy the insurance. I prefer to take the risk. And this is just one particular farmer's preference. Another farmer might have a different preference here. So for example, another farmer might be saying that, even for $7,000, I'm still gonna buy the insurance. I really don't want to take the risk of getting half of the chance of the 4,000 profit. So that farmer will take that 7,000 payment. So every farmer is different. So this depends on the decision maker's preference or risk aversion level. There are a lot of criteria that we can use to help the decision maker make the decisions. One is called expected utility or expected profit. And under this expected profit, there's actually two methods to analyze the expected utility. One is EV, or the mean variance. So E is expected value or mean, and V here is variance. And we will spend quite some time on this method. And here I listed other methods here, stochastic dominance. You will need some statistics knowledge to perform this analysis. It will require you to know the CDF, the cumulative density distribution or cumulative density function. We will not cover this method here. And there are also other criteria. For example, the max-min criterion, where the decision maker will choose the highest minimum profit. So the reasoning is like this: if everything probably goes wrong, so I better prepare for the worst case scenario. And there are also other criteria again, but in this course, I will just cover this EV analysis. But it's good to know that there are other criteria available out there. So under this expected utility, to do the EV analysis, we first need to know what is utility. So you probably have already heard this from your elementary economics course. So this concept of utility is central to economics. And usually, utility is a level of satisfaction or happiness. And so when we consider a set of alternatives facing an individual, and the individual has a preference ordering among those alternatives, then a utility is able to represent those preferences. If we can assign a real number, for example, 5 units of utility or 10 units of utility, if we can assign a number to each alternative so that the assigned number is consistent with our preferences, then that will be a good utility function. So here we have, here I have two alternatives here, alternative A and alternative B. So two alternatives here. You can think of A as good weather and B as bad weather. And the decision maker will prefer good weather over bad weather. So A is good weather and B is bad weather. So here, this is not the inequality sign. This means it's a preference. So the decision maker, the producer, prefer A over B. And this is the inequality sign here. So a good utility function will be when you prefer A over B, then the utility of A is greater than utility of B. So we, in our example, we can assume that the decision maker will always prefer good weather outcome than the bad weather outcome, so that the utility got from the good weather is greater than the utility got from the bad weather. So when we have two risky alternatives here, for example, if we have A1 and A2, then you can think of this A1 and A2 as, for example, A1 as growing canola and A2 as growing wheat. Both are risky actions. And if that's the case, then how will the producer decide to grow canola or wheat? Then if A1, if canola is having a greater expected utility associated with it, then the grower will prefer canola over wheat. So again, here is preference, prefer canola over wheat when the expected utility of canola is greater than the expected utility of wheat. It might sound a little bit abstract here, but let's use graphs to help you better understand what is expected utility. And you have to be careful here that expected utility and expected profit are different things. And let me show you why. So here we have a graph of a utility function. So this black
solid line is the utility function. It probably, you can think of this as a function of U equals to, let's say this is profit to the half. So something like that. It could be a different function form. So on the horizontal axis is your profit, and on the vertical axis is the utility level. And when bad weather happened here, the producer got 4,000 of profit. Let's call this pi 0. And when good weather happened, the profit is 16,000. Let's call this pi 1. So those are two different profits, and each have 50% of the chance or probability equal to 0.5 happening. So those are two risky outcomes. Pay attention here, the expected profit, or you can say the mean profit. And I hope for now you are comfortable with calculating the mean or the expected value. So here, those 2.5 are the probability of good weather and bad weather, and this is a profit under bad weather. This is a profit under good weather. So if you calculate that, then your expected profit is 10,000, and that's this value here. So this is the expected profit. And the utility of this expected profit is actually when you first need to find out what is the expected profit, and then you go straight up to the utility curve. So this black curve here, you go back to that curve and then find out a point along that curve, and you go horizontally here, and that is the utility of expected profit. So again, here, the expected profit is here is 10,000. The utility of the expected profit is here on this point. You have to find out go horizontally here and find out that level. That is the utility level. And for pi 0, 4,000, if bad weather happen, the decision maker also have a utility, and is this number here. And if good weather happened, then it's this point, and that's the utility of good weather, of the profit got from good weather. And here, what I have shown you is the utility of expected profit. Here, a different concept here is expected utility. So again, here is expected utility. In previous slide is utility of expected profit. So again, in order to calculate the expected value, I hope you still remember, is the probability times the value. So if we're calculating expected utility, then we have this probability times the utility of bad weather happening. So here, this point is the expected utility. And pay attention here that this point is not on the utility curve. That is because it's the expected utility. And how we get it here is we actually connect those 2 points. So those 2 points are where your profit is 4,000 and your profit is 16,000. And you go to your utility curve, and then you draw a straight line connecting those two points. And since here the probability of those two outcomes happen is 1/2, so this point, this expected utility point, will located just in the middle of this point and that point. So if you draw a line here, this will be 10,000. However, it is not what you have seen in the previous slide. In the previous slide, the utility of expected profits. So whenever you say utility of something, then that point is on the utility curve. However, here it's expected utility, so it's not on that curve. So we will stop here today, and next lecture I will introduce the concept of certainty equivalence and risk premium.